Hey, everybody. So in this lecture, I'm going to talk about or go over some foundational concepts that we need when we are carrying out hypothesis testing, statistical hypothesis testing. And, in principle, we don't maybe need to know all of the details of, how the statistical tests are done. For example, sort of where the student t-distribution comes from. But personally, I feel like it's really important to understand where that how that came about, how this theory came about, because otherwise it all seems kind of a bit of a mystery. So anyway, today's lecture is the goal is to kind of demystify where the underlying theory of statistical hypothesis testing comes from. Let me go ahead and get the screen share going. Right. So, okay. So what I want to do is basically, we've been talking about statistical inference, which is the idea that we will use measurements of some population to infer information about the population. And remember, we talked about a couple different types of statistical inference. We started out talking about point estimation, where in our case, what we were doing was we were estimating the value of distribution parameters like maybe the lambda parameter for the exponential distribution, or the nu and kappa or k values for the gamma distribution. And we had two different approaches for doing those point estimations. Remember, we had the moment method, where we were essentially calculating the sample mean and sample variance, and then using that information to back out the corresponding distribution parameter values. So that's perfectly fair. The other approach that we talked about was maximum likelihood estimates, or MLE, for those parameter values, and that approach actually is quite a bit more generalizable to other kinds of problems where you're trying to fit a model to data way beyond what we looked at. Well, anyway, that's point estimation, and today I'm going to talk about some of the foundational concepts behind hypothesis testing, which is another type of statistical inference that is especially useful when you're looking at experimental data like the total coliform samples that you've been analyzing at Huntington Beach. So I'm going to start by kind of giving you a conceptual picture of what we're talking about. So imagine that there's a real world population of values. We might say they're in the wild, they're out there somewhere, that are characterized by, we're going to assume, a single population mean mu and a single population variance sigma squared. And to come back to the total coliform example, we might think of the total coliform concentrations in the shoreline waters at Huntington Beach as constituting essentially a real-world population, or a wild population, that we want to learn something about because we're interested in human health risks. In other words, how likely is it that when you go sort of wade into that wild population of total coliform that you're going to get sick? How do we infer information about that wild population? Well, we collect a bunch of observations. So we go out, in the case of Huntington Beach, and we collect a bunch of samples. Maybe we collect, I don't know, some of those sites that you're looking at have somewhere on the order of 1,000 samples at a given site. So a little n here is 1,000. So we've got 1,000 different realizations of total coliform from the beach. Again, that involves collecting a sample of the water and then analyzing that sample, and then you get a single TC value, and the next day you come back and do it again, and you do it 1,000 times, and eventually you have 1,000 samples from that wild population. Well, what do you do with all that data? Well, one of the things that you can do is basically something you learned back in high school. You can calculate a sample mean, which is indicated here by the little X bar, which is just 1 over the number of samples that you collected times the sum of all those values. The other thing you can do is calculate a sample variance, indicated here by S squared, which is essentially 1 over the number of samples you collected minus 1, times the sum over all those samples of the centered second moment of the data. So you take each individual measurement, subtract the mean and square it, and then you sum over all of those samples. And so basically you've got the observations of the wild, you take those observations, you calculate a couple of statistics, the sample mean and the sample variance. What you'd like to be able to do then is infer information about the population from those sample mean and the sample variance. Like, for example, we might be interested in the hypothesis that the population mean mu is equal to a very specific value mu naught. That would be hypothesis H0, or the alternative hypothesis H1, or maybe you could call it HA, is that the population mean is not equal to that mu naught. So anyway, the point is, how do we use information that we've extracted from our observations, that is these x bar and s squared values, to infer or allow hypothesis testing about the population? So that's kind of the context in which we try to, what we need, some foundational information about how accurate these estimators, this sort of sample mean and sample variance, how accurate those estimations are of the population mean and the population variance. And so today's lecture really is about thinking about the estimations, how these estimates relate back to the population values that we're trying to estimate. Okay, we're going to start or focus in first on the sample mean. And so we want to learn a few things about what it is that we're getting when we compute this sample mean here. And we're going to basically approach it by trying to answer a couple of questions. So the first question that we're going to try to answer is the sample mean an unbiased estimate for the population mean? And by unbiased, what we mean is that the expected value of that sample mean is going to be equal to the population mean. Another way to think about it is that if you collected, thousands and thousands and thousands of samples, that eventually the sample mean that you calculated would be a closer and closer approximation of the population mean. So here we have to think a little bit about the sample mean. Now, if you think about the sample mean, what we're doing is we're going out and we collect a bunch of samples, n samples, and then from those realizations of the sample values, we calculate a corresponding sample mean. Now, xi here are, of course, realizations of a random variable, which is, the sampling of the population. And so if we went out and collected another n samples, and then we calculated the mean again, it's very likely we're going to get a whole new set of realizations. So we're going to get another sample mean. And, if you did that 10,000 times, so you went back to the beach and you sampled, say 100 samples, and then you did that, 10,000 times, or, 1,000 times, you would get essentially 1,000 different estimates for the sample mean. And where I'm going with this, or what I'm trying to illustrate, is that the sample mean itself is a random variable. That is, it isn't a single value. In fact, it's a realization. Any particular sample mean is a realization of a random variable which has some sort of distribution. So anyway, that's kind of the first realization, is that this sample mean is actually a random variable because it's calculated from random variables. If it's a random variable, that means that we can think about taking the expectation or the expected value of that random variable. So now we're treating, so little x bar was a specific realization of the sample mean based on a set of n samples from say the beach, or from whatever process you're interested in, that wild population. Well, we can talk about taking the expected value of the random variable for the sample mean, of which this is a specific realization. And basically that would involve then substituting for the random variable sample mean the definition of the sample mean, which is 1 over n, times the sum now of that random variable I over all I running from 1 to n. And the thing to remember is the expected value operator is a linear operator. It's just the first moment of whatever's inside the bracket. And so that means that the prefactor here, 1 over n, just kind of pulls out of the expected value. And furthermore, because expected value is a linear operator, it passes through the sum. And so you end up with 1 over n times the sum from I equals 1 to n of the expected value of the random variables for the samples that you've collected. Now, if it turns out that you're sampling the same population every time you collect a sample and analyze it, then basically you're taking the expected value of the random variable for your samples, which of course by definition is the population mean. So the expected value of that random variable of the samples that you collected from the population has to be equal to the population mean. And if you think about that, the population mean is just a constant, it's some value. So you're summing the population mean from I equals 1 to n, which is the same as basically taking n times the population mean. And so now you have n over n, which is of course 1. And so this all equals the population mean. So the bottom line is the expected value of the random variable for the sample mean is exactly equal to the population mean. And what that implies is that the sample mean is calculated by this formula is an unbiased estimate for the population mean. The central tendency of that sample mean is going to be the population mean. Okay, so the next question that we might ask is, what is the variance of the sample mean around the population mean? So that's kind of a strange thing to think about, but since the sample mean is a random variable, it's going to have some sort of distribution, which means we can talk about the variance of the sample mean around the population mean. We know that the central tendency of the sample mean is the population mean, but how is that sample mean distributed around the population mean as measured by the variance? Well, we can basically play the same game. So remember that our sample mean is a random variable, so we can take the variance or the centered second moment of that sample mean. And so that would just involve taking the variance of our formula for the sample mean. And remember, the variance is the centered second moment. So we've got a constant inside the variance operator here because it's essentially that operator is squaring what's inside the bracket. We can pull out a 1 over n squared from the variance. And we're left with the variance of the sum of the random variables xi. And here's the key point. If these the random variable for the samples that we collected are statistically independent. So you can think about, again, relative to the Huntington Beach example, if every time you dip the bottle into the water, you're essentially collecting a measurement which is independent from all previous measurements, then one of the theories that we talked about earlier says that we can basically pass the variance in through the sum. So we can just move that variance inside the sum if xi are statistically independent. If they were not statistically independent, then actually we'd end up with some covariance terms over here. So anyway, that means that this expression, under the condition that xi are statistically independent, becomes the sum over I equals 1 to n of the variance of xi. And of course, we recognize that as the definition of the variance of the population, the wild population. And so that's just a single number. It's sigma squared. And we're summing it n times, which is the same as multiplying n times the variance of xi. And so that means that, and of course, the variance of xi is just sigma. And so that means that the variance of our sample mean, that's the variance of x bar here, is equal to the variance of the population divided by the number of samples that we collected. And that's really pretty cool. Basically, it means that the spread of our means around the population mean is going to be equal to the variance of the population divided by the number of samples that we collect. So the more samples we collect, the more tightly our estimates of the mean will center around the population mean. All right, so we've talked about the expected value of the sample mean. That's just equal to the population mean. We've talked about the variance of the sample mean, which is equal to the variance of the population divided by the number of samples that we collected. Now let's go a little bit deeper and ask, what is the distribution, the probability distribution of the sample mean? And here basically we can do a little thought experiment. So if the true population or the wild population that we were sampling from was in fact itself Gaussian, then from our previous results, we know that basically if you take the sum of a bunch of Gaussian random variables, you get a new Gaussian random variable. That was one of the things that we derived, probability distributions that we derived in chapter 4. So that would imply that the mean of those samples would itself be normally distributed. However, even if the wild population or the true population is not Gaussian, we know from the central limit theorem that in the limit of a large sample number, the derived distribution for the sample mean will also be Gaussian. So we talked about this. Basically, the central limit theorem says that if you have an essential set of random variables that are each distributed not necessarily normally, when you sum up over many, many of those random variables, you end up with what approaches a normal distribution. And that's essentially what we're doing when we're computing the mean, right? We're taking a bunch of those samples or realizations of the individual random variables, and then we're summing them together and dividing by the total number. And so we would expect that in the limit of large sample numbers, we would end up with a mean which was normal. Thus, either way that you sort of think about it, either the underlying or wild population is normal, we're going to get a normal distribution for the means, or it's the underlying or wild population is not normal, but because of the central limit theorem, the population of sample means is going to be normal. Either way, we should end up with a normal distribution for the sample means. So in the case where we know the population variance, then we can write out kind of our final result. This really combines the sort of three results that we've gotten so far about the population mean. We computed its expectation, which is the population mean. We computed its variance, which is the population variance divided by the number of samples. And we've also concluded that the sample means should be normally distributed. And so that implies that the sample mean random variable x bar is going to be normally distributed with a mean of the population mean and a standard deviation of sigma over square root n. Another way to write that is just to derive the standard normal variate. We know that for any normal distribution, we can write a corresponding standard normal variate, which I'm indicating by z bar here, which is just the random variable for the sample means minus the population mean divided by the variance of the sample mean, which is the sigma over square root n. And so again, this is the standard normal variate, which implies it's normally distributed with a mean of 0 and a unit standard deviation. And here's kind of an illustration of what I'm talking about. So this is basically the probability density function that we're predicting for the sample means. So again, the random variable in this case is x bar. It's the sample means random variable. And little x bar is a specific realization of that random variable. And we're plotting the probability density function for that sample mean random variable against the sample mean outcome. And you can imagine, because we know that the expectation of the sample mean is the population mean, that basically we're going to have that distribution centered around the population mean. And we know that it's normally distributed. So this is a nice normal distribution here. And what we're showing is that the shape of that distribution, and in particular, the dispersion of the distribution around the population mean, is going to depend on the number of samples. And why is that? Because if you go back to the parameters for the normal distribution here, basically the standard deviation of the sample mean is going to be sigma divided by square root of the number of samples. So the larger the number of samples, the smaller the standard deviation will be around the population mean. And you're seeing that here. So we basically are plotting two probability density functions or normal distributions for the sample mean, one with n1 samples, another one with n2 samples, where n1 is less than n2. And so basically for the case where we have fewer samples, we're going to have larger dispersion around the population mean. So our our sample mean is going to be more dispersed around the population mean. For the case where we have a larger number of samples, so we went down to the beach and we worked a little harder, we collected more samples, we're going to tighten that up. So our distribution of sample means is going to be more tightly clustered around the population mean. Okay, so basically the discussion that we've had so far, quite a few of the results, kind of assume that we know what the population variance is. And you might ask, where did that come in? If you look back at our assumed distribution for the sample means, basically you can see that we've got the population variance on the right-hand side here. And so basically that means in order to compute this distribution, we would have to know the sample variance. I mean, the population variance. What if we don't know the population variance and we have to approximate it by the sample variance? Well, coming back to our conceptual diagram, basically in that case, the first question that we have to answer is, how accurately does our sample variance reflect the population variance, right? Because we've already talked about how well the sample mean approximates the population mean. So in the case where we don't know the population variance, we need to figure out how well S squared approximates sigma squared. And really the first step toward answering that question is going to require deriving a probability distribution for that sample variance. And so I'm going to kind of go through a sequence of ideas that really is just borrowing from chapter 4. All we're doing is trying to express the sample variance in terms of variables for which we know the probability distributions, and then we can derive that probability distribution for the sample variance. And I'll tell you the answer, right now, so that as we go through, you kind of know where we're going. Basically, what we're going to find is that the sample variance is distributed according to what's called a chi-square distribution. And that chi-square distribution that is actually derived using exactly the same techniques that we described in chapter 4 from the results that we just showed for the sample mean. Okay, so how does that work? So basically, we start with the definition of the sample variance, and we recognize, just like with the sample mean, the sample variance is going to be a random variable. So if you went out and collected 100 samples and you calculated the sample variance, you get one answer. And then you went out and collected another 100 samples from that same population. Because those samples would be different realizations of the population, you'd end up with a different variance. And so basically you can imagine there's going to be a distribution of variance values, and it's that distribution that we're trying to derive. That's the chi-square distribution that we're going to try to derive. So it all starts by basically writing out the sample variance as essentially a formula of random variables. And so on the right-hand side, we have the random variable for the realization of each individual sample. That's xi. So we go and collect a sample, and we get a random variable giving us a particular realization. And then also we have the random variable for the sample mean. That is, if we had a bunch of samples, say n samples, we'd calculate a corresponding sample mean, and that too would be a random variable. So the thing to really recognize, and this gets back to our derived distribution, is that the dependent random variable in this case, the sample variance, is a function of two random variables. Actually, they're independent random variables. One is the random variable for each realization of every sample, xi, and then the second one is for the mean of those samples, x bar. And so we need to figure out how these are distributed and then derive essentially distribution for the variance. There's a little bit of math that kind of goes ahead of that. And so let's just kind of run through that quickly. Basically, going from here to here, we just multiply n minus 1 on both sides. And then we also can rewrite this term a little bit differently. So we're going to basically subtract the population mean from both of these random variables, xi and x bar. And in the next step, we basically just carry out this squared term. So we end up with this first term squared minus 2 times the cross product between the two terms. and then finally that last term squared there. No surprises. And then now we can kind of look in more detail. Basically, we've got the sum of three terms, 1, 2, 3. So we can distribute that sum between the three terms. And we also can recognize, at least for this cross product term here, that this quantity here is just a fixed number, right? It's just the random variable for the sample mean minus the population mean, and it's not going to depend on the index I, so we can just pull it out of this sum here. So we pulled that out. And the next thing we can notice is that if we looked at what's going on here, we see when we distribute the sum between these two terms, we basically have the sum of the random variable xi, which is just going to be n times the random variable for the sample mean. And then if we move the sum over to the population mean here, we're going to have the population mean summed n times, which is the same as n times the population mean. So the bottom line is that we can basically rewrite both of these terms as n times x bar minus mu, and so we end up with 2n times x bar minus mu squared. And basically, we can see a very similar thing going on with this last term. Again, if we look at what we're summing over in the sum, we can see that there's no index. So basically, this is a constant as far as the sum is concerned. We're just summing this thing n times, which is the same as writing n times that quantity. So we've got this quantity here. Now look, you can see that this quantity and this quantity can be simplified, right? Because they're exactly the same, except you've got -2 and +1 essentially. And so that becomes minus n times the quantity x bar minus mu squared. So kind of this is where we end up after all of that algebra. Sorry that it's kind of a mess, but I wanted to work it out just in case you were curious and wanted to know how that worked. So basically we can write, and what we're trying to do really is we're trying to write the variance in terms of the random variables for the deviation of the random variable from the population mean for each individual sample, in this case, summed over all samples, minus n times the deviation of the sample mean from the population mean, and both of those are squared. So I just moved that same expression to the top of this next page. And there's only one more sort of like algebraic manipulation we need to go through, and that is just dividing both sides of this equation by the variance, the population variance in particular. And when we do that, lo and behold, we've seen this quantity. We know what this quantity is here and also this quantity here. Let's start with this one. This one, if we just kind of scroll way back, way back, way back. So this quantity here is the standard normal variate for our sample mean, right? And we know that that is normally distributed with a mean of 0 and a unit standard deviation by definition of the standard normal. So let me kind of scroll all the way back to where we were. So we can replace this thing with z bar. And we know that that is a standard normal variate, so it's distributed as n01. Likewise, if we look at this, what is this? This is basically is the random variable for every sample. And we know that well, we can assume if the underlying or wild population is normally distributed, then basically this random variable xi is going to have a mean. It's going to be a random variable. It's going to be normal, and it's going to have a mean of the population mean, and it's going to have a standard deviation of the population standard deviation. And so under those circumstances, that is, the wild population is normally distributed, so that is definitely an assumption here. This quantity here is going to be the standard normal variate too. It's going to basically be distributed as a normal distribution with a 0 mean and a unit standard deviation. So that's what I'm trying to say. Basically, now we've expressed the variance, the sample variance, normalized by the population variance in terms of the sum of two quantities squared, one of which is zi, which we know is a standard normal has a standard normal distribution, and that's what that squiggly means. It just means that this quantity is distributed according to this distribution, which is a normal distribution with a 0 mean and a unit standard deviation. And also this standard normal variate here is n01. So if we were deriving a distribution, basically we know the distribution of this guy, we know the distribution of this guy. This is our G formula, and that's what we're trying to derive a distribution for on the left-hand side. And in fact, we can go back in time and remember that we worked a problem a little bit like this, example 4.8. And back in the day, what we showed is that you had a dependent random variable v, say, which was the sum of two independent random variables, x and y. And the formula basically was that v was proportional to each of these random variables squared. And these random variables, x and y, were standard normal, distributed according to the standard normal, or we could say that they were standard normal variates, x and y. Basically, what we showed in this example is that then the derived distribution for v is going to be what's called a chi-squared distribution with 2 degrees of freedom. You see we've got two variables here, x and y, two random variables, and we end up with a chi-distribution of 2 degrees of freedom. And so you can kind of guess where this is going, that basically if you had a sum of n random variables, each of which were squared and each of which were standard normal distributed, you would end up with a chi-square distribution with n degrees of freedom. So that's kind of where we're going. And in fact, that's exactly right. There's a cool little theorem that basically says if you have n random variables, z1 through zn, that are all standard normal variates, that is, they are distributed according to the standard normal distribution, n01, then the sum of their squares follows a chi-square distribution with n degrees of freedom. So basically, what does that look like? So in this case, where we have the dependent random, we're just kind of generalizing this result here. So in the case where we have a dependent random variable, which is the sum over n xi random variables each squared, and each of these are distributed according to the standard normal distribution, v will will follow a chi-square distribution, which is indicated by this symbol here. So chi-squared with n degrees of freedom. And the probability density function for a chi-square distribution is indicated here, where that quantity there is just the gamma function. And this is what the chi-square distribution looks like. So we're just plotting the chi-square distribution against C. And you can see basically that in this case, the chi-square distribution has only essentially one parameter, and that's f, the degrees of freedom. And so depending on the choice of f, we get very different shapes for the chi-square distribution. So when f is equal to 1, basically we see that the probability is bunched up right near the origin. And then as we increase the degrees of freedom, we see that sort of spread out further and further. So let's come back to the problem. So we had something kind of similar. We had the variance expressed, the sample variance expressed on the left-hand side, and then that was expressed as the sum of the square of zi. So this looks like it would go like a chi-square distribution with n degrees of freedom. And then we had a single standard normal variate squared at the end here, which we would then predict from our theorem goes or is distributed like a chi-square distribution with 1 degree of freedom. And so we need one more theorem, and basically that states that if you have the sum of two chi-square distributions with degrees of freedom p and q respectively, sorry, let me go back, that the sum of those two is also a chi-square distribution with the degrees of freedom p plus q. And so basically in this case, we don't have p and q. P is going to be n because we've got, we're summing over n of these standard normal variates squared. So we're going to have p is equal to n in this case, and then q is going to be equal to 1 because there's only one of these standard normal variates, in this term. And so we have essentially n minus 1, and so that means that the random variable for our sample variance is going to be chi-square distributed with n minus 1 degrees of freedom. And if we let f equal to that degrees of freedom, or n minus 1, then we basically conclude that this is the relationship between, or this is the distribution for our sample variance. Okay, so we that was a lot of effort to basically determine that in the case where we do not know the population variance, that the sample variance that we calculate from our data is going to be distributed as a chi-square distribution with n minus 1 degrees of freedom, where n is the number of samples. All right, so now that we know how our sample variance is distributed as a chi-square distribution, we can then say, okay, well, in the case where we do not know the population variance, how is the mean distributed? So previously we showed that the mean, our sample mean was distributed as a normal distribution in the situation where we knew the population variance. But in the case where we don't know the population variance, we need still to determine how the sample mean is going to be distributed. And in order to do that, we're actually going to basically play the same game. We're going to derive a new distribution for that sample mean based on the distribution we just derived for the sample variance, that is the chi-square distribution. Okay, so given the distribution of the sample variance from our previous step, the chi-square distribution, our goal is to find the distribution of the sample mean. And so here we're going to kind of proceed in steps. So first, we're going to remember that when we knew the population variance, a couple slides back in the old days, we were able to write down a standard normal variate for how close the sample mean approaches the population mean, which was this guy here. And remember that just is a standard normal variate, so it's distributed like N01. We can write a similar expression for the case where we use the sample variance in place of the population variance, and we're going to call that a t statistic. So basically, we just replace the population variance with this, I'm sorry, not variance. We replace the population standard deviation, or the square root of the variance, with the sample standard deviation, S. And so we're going to call this the t statistic, just like this might have called a z-bar statistic or a z-score. And actually, that is one way to call it. All right, so then if we're interested in understanding the distribution of our sample mean, x bar, really in this format, that translates to asking the question, how is t distributed? And so what is the probability distribution for t? And remember, we know the probability distribution for s, or we imagine we can calculate it because we know that s squared goes like the chi-square distribution. Sorry, go back. And we also know, well, we don't know the distribution for x bars, so that's something that we're going to try to calculate, the distribution for that. So anyway, here's kind of the bottom line. We know that t is given as this expression, and we want to find out how it's distributed. And we know from previous slides that z bar is a standard normal variate, so we've got that information going for us. And we also know that the variance, which we're expressing here in a normalized way in terms of v, is distributed like a chi-square distribution. So we basically, the goal here, or the master plan, is to rewrite t in terms of z and v. And since we know the distributions for z and v, we should be able to derive a distribution for t. And actually, that's called the student t distribution. So I just rewrote the same expression at the top of the slide here. So the relationship between t, z, and v can basically be developed by noting that if you take the square root of v over the degrees of freedom, so you bring the degrees of freedom over to the left-hand side here, and you take the square root, that's just going to be equal to the sample standard deviation divided by the population standard deviation. And so what we'd like to be able to do is basically take the ratio of this thing and our z bar, which we know is is distributed according to the standard normal, to end up with the t statistic. And in fact, yes, we can absolutely do that, because if we take z bar and we divide it by square root v over f, we're going to recover our definition of the t distribution. And so that's the thing we were looking for, right? The rest is just math because we want to know the distribution for t, and we've expressed it in terms of z bar and v, for which we know the distributions. We know z bar is distributed as a standard normal, and we know v is distributed as a chi-square distribution with degrees of freedom f. And so basically, when you take this function g, right, relating the dependent random variable and two independent random variables, and you plug them into equation 4.13 in the book for deriving the distribution, you end up deriving a new probability density function called the student t distribution, which is shown here. So basically, the net result is in the case where we don't know the population variance, so we're using the sample variance as an estimate of the population variance, the sample mean is going to be distributed around the true population mean according to this t statistic, which is distributed according to the student t distribution, for which the PDF is shown here, and f is the degrees of freedom, just the number of samples minus 1. And you can see if you look at the right-hand side here that basically this probability density function has a single parameter, which is again the degrees of freedom. And so that's, I just reproduced what we saw on the bottom of the last page. But what I wanted to show you is in this graph here, we're comparing the t distribution to the standard normal distribution. So remember, in the case where we knew the population variance, we could say that the sample mean was distributed around the population mean according to the standard normal distribution. Well, that corresponds to the situation where we have an infinite degrees of freedom for the student t distribution. In that case, when f goes to infinity, the student t distribution essentially becomes the standard normal. And so that would be sort of the same, another way of saying that you kind of had perfect knowledge of the population that you were sampling because you collected an infinite number of samples. And under those circumstances, you kind of know the population variance because you really know everything about that population. So in that limit, then basically the distribution of means about the population mean, when you put it into a standard normal form, is going to just be n01. However, if we don't have an infinite number of samples, say we had 7 samples, which gives us a degree of freedom of 6, or we have 3 samples, which gives us a degree of freedom of 2, what we see is that the probability density progressively declines, at the position 0 here, which corresponds to the sample mean equaling the population mean. So it's less likely we're going to get that value. And instead, more the probability is going out into the tail here. So it's more likely we're going to get, we're going to sample values which are far away from x bar equaling the population mean. So here's kind of a summary of the foundational principles that we need for hypothesis testing, which I'll go through in the next presentation. Remember, we start with the formulas for the sample mean and the sample variance, which are expressed here in terms of random variables, recognizing that the sample mean itself is a random variable. That is, every time you go out and sample n samples from a population, you're going to get a different sample mean, and so it's distributed in some way. As then that is also true for the sample variance. We're going to get a different sample variance every time we sample the same population n times, and so it too is a random variable. We showed that the expected value of that random variable for the sample means is equal to the population mean, which is a very good sign. It just means that this particular formula for the sample mean is an unbiased estimator of the population mean. Likewise, we showed that the expected value of the sample variance is going to be equal to the population variance, indicating that this particular formula for calculating the sample variance is an unbiased estimator of the population variance. In the event where we know the population variance, we also showed that the sample means are normally distributed around the population mean mu with a standard deviation of the population variance, or sorry, population standard deviation divided by the square root of the number of samples that we collected. And that was kind of cool because basically we can see then our distribution of sample means around the true population mean is going to get tighter and tighter as we increase the number of samples that we're using to calculate that sample mean. And because X bar is normally distributed with mean mu and standard deviation sigma over square root n, that automatically implies that we can construct a standard normal variate, a corresponding standard normal variate, which is going to be normally distributed with a mean of 0 and a unit standard deviation. On the other hand, in the case where we do not know the population variance, we're using the sample variance as an estimator of the population variance. The first thing we wanted to do was determine the distribution or probability distribution for the sample variance. And what we found is that this quantity here, the sample variance over the population variance times the degree of freedom, which is defined as n minus 1, is going to be distributed. That's what that little squiggly thing means, as a chi-square distribution with n minus 1 degrees of freedom. I've just rewritten that here, where the degrees of freedom is indicated by f. Again, s squared over sigma squared times f is going to be distributed as a chi-square distribution with f degrees of n minus 1 degrees of freedom. And once we figured this out, we could then conclude that the distribution of the sample mean around the population mean is going to be given by the student t distribution. So for that, we define a t statistic, which is basically the deviation of the sample mean from the population mean divided by the sample variance divided by square root times the number of samples that we've collected. And this particular statistic is going to be governed or is going to be distributed according to the student t distribution, for which the PDF is shown here and depends only on the degrees of freedom f. And I should say also that the chi-square distribution depends only on the degrees of freedom f as well. So if we come back to where we started, remember we have this real world population we're trying to learn something about. It's in the wild. We take a bunch of observations. We calculate a sample mean and a sample variance. And then we're trying to use that information to basically hypothesis test about the population in the wild. Basically, what we've done in this particular lecture is think about how accurate the sample mean and the sample variance are as estimators of the corresponding population values, that is the population mean and the population variance. And so the next talk is going to focus on actually carrying out the hypothesis testing and kind of the mechanics of that. So with that, I will say goodnight and basically finish up. Okay. Hope you enjoyed. Bye.